minutes for me to open. Okay, here we go. Number 2, you guys can see signs. Number 10, you were trying to, I believe, solve the triangle, so you have to kind of go and find all the pieces of information you needed, side C, angle B, angle A. Number 34, you were also solving. The only way to solve that one was law of cosines because you had all 3 sides, and I think the beginning of homework was pretty much all needing law of cosines for at least part of it. But double check if you did transition to law of sines, are all of your answers matching up? You needed to start with law of cosines. Maybe you could have gone to law of sines after that. Number 36, you had a choice. Right around here, you got to be able to choose which one. Since you had 2 angles, law of sines would have been the easiest way to go. And even more than easy, I think it was the only way that you could have gone. You can see your angle A, your side B, your side C. Wasn't ambiguous. You had 2 angles, so didn't have to worry about that whole weird 180 minus. Did I go too fast? Which one do you need?
Isn't it supposed to be 180 the angles?
Yeah, so we have 150, 160. Ooh, 160. That only adds up to 170. Oh no, that's right. Sorry. These aren't angles. These aren't angles. Oh, got it. Yeah, you're like, no, it doesn't work. Yeah. That was side A. So we had angle, and they subtracted from 180, and that's how we got 161. Good check. Okay, number 38. Oh, sorry, too fast. So you have your angle, and then you have your side, and then you have your side. Okay, number 38, you guys are just throwing into the area formula, ending up with 399.04. Number 56, plugging into law of cosines would not have been bad. It shouldn't have been bad. Let me zoom. There we go. 56, plugging the law of cosine should have been pretty easy. The hard part was when they asked you in letter B to get x by itself. You're like, you gotta be kidding me. How do I get x by itself? Like law of cosines, no big deal. How do you get x by itself? Guys, come on. You recognize it. What'd they do? Plus the 9 squared, root b for 9 squared. You don't want to hear me saying this voice, but they did quadratic formula. What was weird is that they had to ask themselves, what is there besides the x? 3 and cosine theta. They had to steal that whole thing for their A was 1, C was negative 46.75, B was negative 3 cosine. So you see how that was showing up in the formula. They're like, well, sweet. If you found that, guess what? You can throw that into a calculator and graph it. And not only can you graph it, but you can also find the max of it with your second trace max feature. But the key was the quadratic formula. So if you guys got a little lost on that one, I understand it was hard to solve for x, especially with that cosine of theta. You were like, what? But you just made that 3 cosine theta your b for your a, b, c in the quadratic formula. And then this should have been pretty straightforward. If you have more sides than angles, it's always law of cosines. More sides than angles. The one exception is the ambiguous case. The ambiguous case, we're going to do law of sines because we can do that sine inverse and 180 minus sine inverse to see if it truly has 2 options or not because it's ambiguous. All right, I'm going to go ahead and go over homework questions in just a second. You guys look back over the evens and the odds, the questions you might have. Just getting shown a couple things that help me Okay, let me open up the book. So section 6.2, I don't know why that didn't open. Let me try to hit the tab one more time. There we go. Is there anything that you guys need to see from last night's evens or odds? Griffin, what do you got? 51. Anything else besides 51? You guys, if you do have one? We're going to say 51 too. Anything else besides? Anything else besides 51?
56.
56? All right, I'm going to take a last call after we've done those two questions for anything else that you guys might have come up with. So, starting at number 51, moving to number 56. The nice thing is we got past that parallelogram because you guys asked it yesterday. 51 was weird all because of it having to do with angles, but way more than that, angles outside the triangle that you see. We talked about law of sines and the Leaning Tower of Pisa, and we talked about which examples are hard. The ones that are hard are when you have to go outside the triangle you've been given. This baseball, softball diamond one wouldn't have been hard because they gave you everything inside the triangle. John, I have some algebra grades for you to write down. There are extra algebra grade sheets in the back to get you started. Okay, so that one was pretty straightforward, but Leaning Tower of Pisa definitely was not, and this one in homework definitely was not, because it all had to do with bearings. Now, as soon as you see bearings and things like due west, they're talking about compasses. If they're talking about compasses, we can say if you're in Phoenix, you have a north, south, east, west. If you're in Minneapolis, you have, when you're there, something north of you, south of you, east of you, west of you. And if you're in Albany, you have a north, you have a south, you have an east, you have a west. I know that seems kind of like duh, but that's where you might have gotten lost in this problem because it asked for, it gave you lengths of sides. You probably figured the triangle was somehow important, but check it. They want the bearing. Bearing says start from north. If they don't tell you like north-south or, sorry, not north-south, like southwest or northeast, if they don't tell you something like that, we always start from north, which is weird because in math, we don't start from north. In math, we always start from the positive x-axis. That's how we turn a theta. But when they say bearing, we're not turning that direction. We're going from north instead and north of wherever we are in a clockwise fashion. Everything's kind of gotten turned on end so that this is kind of like our positive x-axis because we're starting there. And that's kind of like our positive y and our negative x and our negative y. It all got like flipped around. So anyway, bearing of Minneapolis from Phoenix. So what is that saying? If you're in Phoenix and if you're trying to head on a bearing of towards Minneapolis, what would that angle be? If you're in Phoenix trying to head towards Minneapolis, what bearing would you have to turn in order to be able to, from Phoenix's north, in order to be able to head to Minneapolis? What they're asking for is this theta, and what makes it so awkward is that theta is outside the triangle. That theta is outside the triangle. So here's where it starts to get a little bit messy. Even if I were to find this guy on the inside, I called this guy theta. Even if I was to find this guy on the inside, which I could do from side, law of cosines, I'll call him phi. Even if I was to find him, I don't know what these two add up to. It's not 90 because I have this extra awkward piece. So actually that angle doesn't help me for this guy. I have to look to another angle in the triangle. And the other angle, my advice would be for us to look would be this guy. We can call him, I don't know, something like alpha. I can still totally find him from law of cosines. I would just need to do, let's see, cosine of my alpha equals. Don't you use the other two sides squared added together? Did you guys get that from the law of cosines homework? So we have our alpha angle right here. So I'm not going to use this side. I think I used the other two sides and I subtract this one. Can you guys back me up really quickly just because I'm not super solid on the law of cosines formulas? Okay, so if I need my a, then I'm going to do my b squared plus c squared minus a squared all over 2bc. And so I need to go ahead and do cosine inverse. Can I find that angle? Yes. But some of you are like, I don't get it. Why are you finding that one to find that one? Can anybody see what I'm doing? to go back to geometry. We had some kiddos in here yesterday that were putting up some problems on the board from 8th grade Chinese math. Lots of geometry. And it was super hard for me to figure it out. So we don't do tons of geometry in America, and it's actually not a good thing, but sadly that's kind of the standard. And so we're preparing you for things like standardized tests and SATs that have some geometry, but not near the level or the extent other countries are teaching math. So you might be like, why is she harping on geometry? Why doesn't she just tell us the answer and move on? Well, it's because, to be honest, in America, geometry is a weakness. What up here could help me figure out this angle outside this triangle?
It's a right angle.
I wish there was a right angle. I could make some. I could like start making little right angles. But to be honest, I think that would make it harder, but that's not a bad idea. I just don't know if it's super apparent. I don't see right angles. But I do see a lot of due east. Spencer, what do you see?
Doesn't the alpha equal the bottom or the left two angles?
You're seeing this right here, right? Those ones? Yeah. But why?
I don't know.
You don't remember? Everybody's due east is going to be parallel. Everybody's due east is going to be parallel. And what's true about parallel lines? The transversal that cuts through. What's true about parallel lines with a transversal that cuts through? When you have alternate interior angles. They're congruent. Now, some people were just looking at the picture and Spencer, I think you just kind of were like, I'm pretty sure it's the same. And you're right. And so actually someone said 90 degrees, and to be honest, it was important. It just, I didn't have any clear 90 degrees except for my north, south, east, west. Wait, I didn't have any clear 90 degrees except for my north, south, east, west. This is 90. So my alpha, take away 90, is going to equal who? Exactly what I did. My alpha, take away 90, take away the northwest 90 degrees, is going to get me my theta. It seems so random a second ago. Like, how are you supposed to get that guy? It makes no, parallel lines. We have a transversal. I know it's geometry. It's actually on the SAT. Nothing else. Reviewing just a little bit of a subject that you guys haven't taken for a while and that Americans are generally weak on. My alpha, alternate interior angles, is congruent to this whole outer. Take away 90. I have that bearing. I have that bearing. So all we have to do is do alpha minus 90, and we have the bearing. Then we still have another bearing. What's the other bearing that we need? Albany from Phoenix. So I say, okay, if you need to go to Minneapolis, what do you turn? Got it. If you want to go to Albany, where do you turn? Well, Albany, wouldn't I need to go from north of Phoenix this way? Wait a minute, hold on. That's not bad at all, because what did we just find in letter A? And if we need to turn to Albany instead, all we need to add in is this guy. So the nice thing is, all I need to do for this one is to go ahead and do theta plus phi, but you might be like, I don't know phi. I know, but he's still just an angle in a triangle. No big deal. We can solve for him. So we can go ahead and find his just by doing cosine inverse of, not that guy, the other two guys. 216 squared plus 368 squared minus the 165 squared all over 2 times 216 times 368. Once again, ironically, just like section 6.1, what made it hard? The geometry. Because as soon as you get outside a triangle, you guys are like, I don't know what to do. Because parallel lines and making, I know in the Leaning Tower at Pisa, we had to make a right triangle. That actually wasn't quite the way here, even though that right angle was kind of the key. We had to think about parallel lines and then transversal. So Spencer, thanks for speaking up, and thanks for the rest of you guys that kind of chimed in and getting us to that point. So all you need to do is find phi, find alpha, and then plug them into our little baby book, and then we got it. Sorry, I never actually wrote theta equals, so some of you guys are just now coming in. You might have missed what we were doing. Bearings say start from north and turn towards the city that you're headed. So both of these were starting from Phoenix. So Phoenix is north and trying to figure out what those angles are. This guy was rough because he was outside the triangle, but if we find this angle right here from the flight path to due east from Minneapolis, then we could say alternate interior angles are congruent. We don't want the whole thing. We take away the 90 from this northwest portion and we just take that east portion to get theta. And then to turn to Albany, all we have to do is solve this last little angle in the triangle and add it to that original bearing from A. Anyway, excellent question. Glad you guys asked. It is a bit messy, and I got to prove a point that it gets rough when you get outside a triangle, but geometry is usually the key. Sorry, 51 was one, and I think 56 was the other. Was that right? I don't know. You guys were the ones asking the questions. Was 56 or 56? Our other one? Okay. Sadly, my book decides to freak out sometimes and just not show pages of a PDF that I paid good money for, but that's all right. So we're going to go ahead and open up the webcam real quick to find that 56. There we go. We're in section 6.2. For those of you guys that came in a little bit late, we already graded the even, so it's on the video, or you can maybe check with someone right around you to get those answers. 56 was the engine design one. Okay, I'm just going to steal a picture of it real quick so we don't have to stay in this webcam because it's slowing down my computer. Let me grab them real fast. Here we go. I already talked about how the quadratic formula was key to solving this one. I was kind of walking you guys through the answer key over here as far as why they did what they did. I think I'm more concerned if you still have a question on it, besides just not liking the quadratic formula. I'm more concerned that you knew how to set up the law of cosines to begin with. So let's just peek at the picture real fast and make sure we knew what we were doing. They told us a few different dimensions, a few different facts about this engine with this connecting rod, and they gave us, you can kind of see the triangle pretty clearly, I think. They gave us the theta as this little angle over here, which is usually our angle A. We have a 7-inch connecting rod, and then we have a 1.5-inch arm over there. And they're just asking us for letter A, just use law of cosines to set up what we've got. But if you notice, we only have 1, 2, 3 pieces of information, and so we needed to go ahead. Oh, there's the x. I couldn't find it. X is that one length that we don't know. But in our law of cosines, we have to use an angle with its opposite side. So some of you, I guess you could have, if you really wanted to, I guess you could have done like cosine theta. Maybe some of you would have done it that way. And you would have done your, what, 1.5 squared plus x squared minus 7 squared all over 2, 1.5. I guess you could have used that one. I mean, you wouldn't have been wrong. I guess you could have used that one. The one that probably more people would have done, or at least that the book did, was the 7 squared equals, and then you had your 1.5 squared plus x squared minus 2 1.5x. 2 times 1.5 is just 3. Wherever you are, that's just a 3. 1.5 squared ends up being, is that 2.25? No. 3 halves and 3 halves is 9/4, which would be, yeah, 2.25. Okay, and that's 49. So we have 49 here, we have 2.25 there. We have our x squared minus 3. Now I'm going to write this weird just for the purpose of what I showed you guys when we were going through the answer key. That's an x squared. That's an x term. I know it's with a cosine, but it's an x term. And I could go ahead and subtract this guy to the other side, and I end up with a good old-fashioned but messy-looking quadratic with an a of 1, a b of 3 cosine theta, and then a c of 46.75. Did anybody get that? 46.75. Cool, because we're acting dead today. So then all we have to do is x equals negative b. plus or minus square root b squared minus 4ac all over 2a. And if you guys notice on the answer key, that's literally what they did. They plugged and shoved, and then they made it look pretty, but whatever, you didn't really have to. Then they went ahead and said, hey, you know what? In the rest of the problem, once you finished that question that they were asking of writing x alone, which is the only way to do that is by quadratic formula, because I don't know how to factor that. I don't even know what it is. They said go ahead and graph it. So to graph it, all we have to say is, oh, y1 equals. Plug in this whole shabam, the whole quadratic formula, into your y1. And what do? As long as you, did they tell you anything about restrictions? No, they didn't. So they went ahead and made it between 0 and 2 pi. If you guys had done a standard window, this would have kept on going a bit further, so you would have seen it cycling a bit more, which kind of makes sense because as that rod is moving, it's going in and out and in and out and up and down. But anyway, they were just caring about the maximum. And so the maximum, if you guys had looked at the graph, maybe you could have counted and known that it was between 8 and 9 and guessed 8.5. You could have also seen that sinusoidal and found the max, and that's 8.5. So, as I was saying earlier, just got to use that quadratic formula. But maybe the picture was weird for some of you, but in law of cosines, I have to do the opposite side with the opposite angle. I have to have them paired together. The only way to set it up would be with theta and 7 squared or with 7 squared and with theta. There was no other way to write it and be correct. With that, kiddos, we're going back to this section 6.3 vectors unless someone has a last minute question that they need to bring up before we move away from 6.2. How are your calculators? They're still okay? All right. We're still in degree mode? I hope so. Otherwise, this section of vectors is going to be a mess. The nice thing is with vectors, though, we get to kind of start off basic because it's so new to you. Mostly. It's so new. Vectors are so new. I said it's pre-physics, so it's like the beginning of one topic in physics. Not all of physics, just one topic. In many crazy ways, which is hard for you guys to know because you kind of probably weren't taught that way in elementary or middle school math. Middle school. Math class, it's a lot like a language class. For you to be able to go to a country and in a remote part of another country and be able to communicate well with the people there, you gotta know the language, so you take language classes. In order to be able to delve into different STEM fields and do problems or explore concepts or do research, you have to know the language with which the information is being given, being shown, the formulas where they come from, or at least how to deal with them. So in lots of different ways. This is a language class where it's like, well, what's the point? Well, I'm trying to teach you some of the language so that you'll recognize it if you ever see it again. Vectors, a little bit of physics, just a little bit. Physics, a very fundamental gen ed class in most STEM majors. STEM, science, technology, engineering, math. Physics is even more fundamental than calc. Physics and statistics are probably two of the main gen eds for almost every STEM major out there. Vectors, just one little concept in physics. What we saw yesterday was, okay, Despicable Me knew it. Well, maybe, okay, whatever. But at least little Vector Villain dude, he was a bit of a nerd. But he knew it, like a line segment with direction and magnitude. If we're talking about vectors or forces, there are a couple things we almost always know. In which direction it's pointed and what magnitude. For instance, the one that we should all be the most familiar with up here, even without taking a physics class, is gravity. Where is gravity pulling you? Down. Right? I mean, that's pretty obvious. I mean, we won't go into the solar system and like the gravitational pull of planets. Like, let's not go there. Let's just say we're on Earth, gravity pulls us down. Which means you throw something off a building, right? Throw an apple off a building, what's going to happen? It's going to go splat, right? It's going to, unless it hits someone on the way, but then it probably still will. It's going to go down, no matter what, right? So gravity, is that something where we know the direction? Sure, it's always there. Is that something where we know the magnitude? Roughly. Gravity technically kind of changes by very small increments depending on where you are in the Earth, but because the Earth might not be a perfect sphere. But anyway, coming back, but gravity, roughly, if you're measuring in feet per second squared, it's negative 32 feet per second squared. We could say it's 32 feet per second squared, but it's pulling down, and so then if you're talking about acceleration, it'd be a negative. Or if it's meters per second squared, it'd be 9.8. Negative 9.8. Not that you have to have that memorized at all. The calculus kids kind of hopefully do by the end of the year, but gravity pulls straight down, and there is a constant attached. So we know the direction and we know the magnitude. Now, for all these other forces that you guys see up here, we were talking about vector diagrams. Once again, it's easiest to be like, well, where is it acting? Well, if I was to zoom in on these kids, these guys, I don't even know who they are, in a roller coaster, we zoom, zoom, zoom. And if I was to tell you that this blue guy, for every single one, this blue guy, normal in physics, I could say in math too, because technically math is like the language. Normal just means perpendicular. It's the force that's working perpendicular to basically the track that you're on. So if we were to, this is getting a little crazy and calculusy, but if we were to talk about just a point on this track and like kind of the trajectory that someone mentioned yesterday, we can call it like the tangent line sort of, even though it's not a circle, there are tangents to things other than circles. That's calculus. But anyway, we can kind of talk about this tangent line. The normal force would be the force that's acting on this car, on these people, at a perpendicular angle. At a perpendicular angle to that track at that point. And I could kind of, like, technically, I think you guys might be able to think of that tangent line as skimming and then go 90 degrees. Think of that tangent line as skimming and go 90 degrees. Think of that tangent line as skimming and go 90 degrees without having taken any calculus. Just be like, okay, whatever, I'm skimming and then I go 90. I'm skimming, and you could probably figure out the path, the direction of the normal force too, roughly, without even having heard about it before today. Just think, okay, skim the track and then go 90 degrees out. Here's the hard part. If we were to only talk about vectors in terms of directions and magnitudes, every single problem would be like the Leaning Tower of Pisa problem and the bearings to Phoenix and Minneapolis and Albany. And how does that sound? I don't even get an answer for that? Come on, you can't even be honest with that one? What does it sound? Bad. Thanks. Sway's been the only one talking today. Who wants all Leaning Tower of Pisa problems? Nobody. Why are those hard? Geometry. Why is the geometry hard? Because it brings in transversals and parallel lines and alternate interior angles, and yeah, we could review all that. But here's the dealio. If we kept in direction and magnitudes, we would have to take all that geometry and we'd have to apply it to all these triangles that are not right triangles, aka not just all the geometry, but all the law of cosines, law of sines. Is it impossible? No. I gave you the Leaning Tower of Pisa problem. A couple of you figured out, the rest of you at least somewhat maybe followed some of it. Or at least the bearing problem, maybe you didn't follow along and do it all yourself, but did you see me do it? It was law of cosines and it was geometry. It was possible. So here's the dealio as we face these vector diagrams. We could just go with the, hey, in what direction and at what magnitude, and we'd have a lot of geometry and a lot of law of cosines, law of sines. Or we could say, is there another way of expressing these vectors? It'd be nice if there was. And someone today, but also in the Leaning Tower of Pisa problem, brought in the whole like, can we do a right triangle? And that's exactly what we're going to do. But before we move this page, once again, to consider all the different vectors or all the different forces, which is one application of vectors, all the different forces acting on a single object at an instant of time, we can think about them, ready? In context of the picture, like, hey, that guy's working this way, that guy's working this way. And we can think about them ultimately all together but separately. We have gravity acting this way, the normal force acting that way. Or we could basically translate some of these vectors around and say, wait a minute, what if we were to think about them together, like here's gravity and how it's acting, And then if I tack on the normal force from there, how it's acting, and then I can do this thing called a net force that says what's the overall result. And the snazzy physics term for the overall result, like the net force in this example, is called the resultant, which hopefully at least kind of makes sense because resultant. And what that technically is an addition of the two other vectors. Now, if I was to call this vector, which we can do, like a lowercase u, I could throw that in for the gravity. I could call this one lowercase v just to be simple and not have to write it all. Then technically what I could say is that the net force, or maybe I would call him R, R would always equal whatever forces I have. Which in this one is just u and v, because we're just talking about those two forces, the gravity and the normal force. But to be honest, we could have all kinds of different forces acting on an object at a certain time. So we could have u plus v plus w plus x. We don't usually use x because we use him in other places. Plus y, same reason, plus c. We could have all kinds of vectors added together, but the problem is the geometric formula, what is now just a triangle because there are only three things at play, two forces, one result, could get really nasty if I start having 3 or 4 or 5 things at play, because all of a sudden it's not a triangle anymore, and I'd have to make little individual triangles for every single one. So technically, even my geometry, law of cosines, law of sines, is only good when you have two forces. If you have more than that, it gets rough. So once again, at the foundation of these vector diagrams and trying to think of, okay, great, the picture shows, but how does that actually translate? How do those go together? What's the overall result? What's the overall force acting on a person at a certain instant in a ride? We would need to try to put all these forces together, and the only way to put them together is, well, I guess we could subtract, but that means something different. We won't even go there. Is to add them, and to add them, we have to get them out of the picture and put them what we call head, like the head of a comet, the head of the vector, to tail, like the tail of a comet, the back end, the tail of the next guy. And we can then go ahead and say, hey, from beginning to the end of the overall is what we can call the net force. Okay, that's a lot of intro. Sorry, it's a little bit annoying in the sense that it's so new. And a lot of these terms that I'm throwing at you are just like, what is she talking about? It's just the beginning of vectors. Yesterday, did we at least get that that doesn't mean go on forever? Right? It means stop. There's an actual length to it. And the length means something, like the magnitude. So over here in this one, which is much more precise than the other one, if I was to look, for instance, right here, this doesn't mean forever gravity. It means, no, this actually symbolizes my negative 32 feet per second squared. And, well, the normal force isn't as great as gravity in this instant. And I think we all know that. I think we know that gravity is the strongest right here when you're upside down, right? But gravity is stronger than normal force. Why? Because it's longer. The length has to do with the strength. You can think of it that way. We talked about how you put little arrows anytime you see a bold letter. This entire section, notes and homework alike. We talked about initial points and terminal points, beginnings and endings of vectors because they're not going on forever. Okay. So let's start talking about some of the basics as far as some of these words that I've been using and some ways of writing them, notations, etc. Let me just give you a chance to not have to listen to me for a while because I'm annoyed with my voice, believe me. And as you guys are writing this, why not? Let's make this practical. Can you guys in your groups really quickly, just random, if you had to choose a college major today, you had to choose it for the rest of your life, what would it be? Ready, set, as you're writing, go. Well, there's so many weird college majors out there, maybe you don't know them all, but if you had to at least choose a field, or at least a somewhat career, you had to choose today. Don't worry, you don't have to actually choose it. Someone hasn't shared. Come on, someone louder, or someone more vocal, or someone who's at least more obedient. Be like, hey, what would you do? Has everybody had a chance to share? If not, at least a little more obedient. Just reach out and be like, what would you do? What would you choose? You don't have to be bold, just be obedient. And then pick on random people and ask them what someone in their group said, so you better remember it. I'm not going to ask you what you said, I'm going to ask you what they said. And if you never ask them, ooh, that's awkward. And your entire group, not just beside you, in front of you or behind you as well. For instance, I could ask Kayla what Ivy would choose. I could ask Spencer what Laura would choose. I could ask Emma what Vanessa would choose. I'm not doing it, so I'm giving you a little more grace. Learn what they would do. You had to pick one today. College dropout is not a major. Random millionaire, not a major either. I'm saying if you had to choose a college major, an actual college, a 2-year, 4-year, could be a 2-year degree, could be a trade someplace, I suppose. Alright, so wait, what would Lucas choose? Something in tech. Okay, cool. It would need physics. Kimia, what would Ariana choose?
No college.
Oh, that wasn't a degree. Ariana, you gotta choose one. But good job knowing her answer. If you had to choose one, just something right now. With design? If you were going into computer science at all, you would need physics, but maybe not. Depends on which way you would go. Aiden, what would Nathan choose? Yep, definitely physics. Justin, what would Dylan choose?
Something in business.
Maybe not physics. Definitely statistics. Oh, that's fun. And then business calc. Business calc. Good stuff. But it's much more specialized than high school calc. Emma, what would Diego choose? Law. You might be able to get away with just college algebra. Nope, stats. You would definitely need stats. Not too bad. What groups haven't I picked up? Oh, you guys. Brandon, what would Sadie choose? Sadie. Oh, that's awful. Kayla, what would Sadie choose? Music? Only if you had to work with synthesizers and like if you actually got into like the programming, would you need physics? Otherwise you may not. Otherwise it might be free. But anyway, you guys kind of get my point, right? I'm not saying that your careers necessarily. Now, if anybody chose engineering, if anybody chose tech, if anybody chose anything science, anything medical, anything physical therapy, anything kinesiology, you would all have to take physics courses. I mean, math isn't obvious, let's not even go there, right? But anyway, a lot of these things, economics, tons of calculus in that one. Maybe not physics, but at least and econ would definitely, sorry Diego, you might get stuck on that one. At least a little bit. But, coming back. Probably, for those of you guys that are in this class, a lot of you will need a physics course. So just hang in there, and I'll give you the best intro I can to this one baby topic. Cool? Here we go. But also, gave you a chance to, well, some of you, Brandon, to reach out and listen to their group and get to know them a little bit better. I'm just kidding. Okay. What do you see? I said a second ago, just think of the length is the. I didn't even rhyme. I was so proud of myself. The length is the. Magnitude is what of an earthquake? How strong? Okay, the length is the strength. It was exciting, but it wasn't. Okay, so the length is the strength. It's how strong. It's how much. Okay. It's always better than the how muchness. Anyway. So if I'm talking about magnitude of PQ, I could also be talking about the magnitude of a vector v. Remember, lowercase letter, I could also do the beginning point, ending point, PQ. It could be the magnitude of vector v as well, either way. But I want you guys to write down that's the same thing as the length of the side. And why am I putting it like that? It stands for course, or it stands for velocity, or it stands maybe for an actual distance, or it stands for maybe how much work is being done, or how much tension is being exerted. It could stand for all sorts of different things. But for you guys, all I need you to think about is the length of the side. We've been talking about triangles. The length is literally indicative of the strength, or the strength is indicated by the length. So however long a vector is, that's how much it is. Now it has to be in certain units, etc. I'm giving to you, but you can show the length. So if something has like a force, I want to go that route. Let's just do a velocity. If something has a velocity of like so many miles per hour, well, 30, I would make it like 3 units, and 20, I'd make it 2 units. Like, I make the length indicative of the strength. Now, equal vectors, this is kind of a big deal, it's kind of not. Do you guys know a second ago how I said something about to make these vector diagrams, you have to actually translate the vectors? The reason we're allowed to do that, the reason we're allowed to move it all around, is because of this idea, which you guys can notice, this picture is not the same thing as this picture, so even though it's more precise than this one, that's like, they're all the same length, kind of, it's still not very precise because the lengths change. That shouldn't have happened. But with this one, I can translate vectors because technically, even though their original position may be important because it's acting on the people in the car, for the mathematical analysis of it, I don't need it to stay that way. I just need it to stay with the same length and with the same direction. And that's what this whole equal vector says. You can move it around if you want. You just have to keep it at the exact same angle, at the exact same, or with the exact same length. You can move it, you can shift it, you just can't flip it, you can't twist it or stretch it. That's going to change it. You can't rotate it, but you can shift it anywhere you want, especially for those vector diagrams. So then you might have something as basic in homework that's like, hey, are these equal? And you're like, oh. Some of you would say, no, they're in different places, but no, they can be equal and be in different places. The position is not what's important for vectors to be the same. So what I would do is some sort of distance formula as far as, wait, distance is length. That'd be the same thing as magnitude. I could find the magnitude of this guy by doing x2 minus x1 squaring and y2 minus y1 and squaring. I could find the magnitude of u, and what would need to be true if these truly were equal? What better happened with these distances, guys? Yeah, they better be the same, but if you guys do some quick math, that's going to be 9 and 4, and that's going to be 9 and 4. They're both root 13. They both have the same magnitude. What else needs to be the same, though? The direction. But if you guys were paying attention, maybe you noticed that a change in y is going to be 2, and a change in x is going to be 3. Maybe you can see that this guy's slope is 2 over 3, and this guy also has, here we go, a change of 2 and a change of 3. We could do a quick little tangent inverse. Oh my goodness, we're seeing a lot of math that's actually like physics formulas that you would maybe memorize one day, of how to find directions of vectors and how to find magnitudes of vectors. Magnitudes are really just Pythagorean theorems. What? Yeah, a squared and b squared. Like the very first day of pre-calculus when I said, what's the distance formula? It's just Pythagorean theorem. If you make a little over, a little up, a squared plus b squared square rooted. And to find angles, we're going to be using tangents because we can say horizontal and verticals as far as horizontal displacement and vertical displacement. And guys, both of them for u vector and for v vector are going to be the same. Yes, they're equal. I know we didn't cover tons and tons and tons of the math, but we did do quite a bit as far as who vectors are, how we write them, how we talk about them with magnitudes and directions, some little different things like subscripts that we're going to be using to be talking about different vectors all at the same time. Some things like resultant vectors are really adding two vectors together. And maybe, just maybe, some of you might start understanding where I'm headed If a second ago I said, man, those pictures are going to be gross with geometry, with law of cosines, law of sines. But if I can break any vector down into horizontal and vertical components, and technically the components of this one, give me one more second. The components of both of these guys would actually be the exact same of going over 3 and up 2. Maybe I can do little baby right triangles instead. Alright guys, we'll do a lot more math on Monday. Get out of here. I'll see you later. Good job. If you get more questions, pick me this weekend for inspiration. I mean, go watch the Khan Academy video. It sounds a little classroom, I believe, Ivy. I'm just saying, there's probably not tons.